Okay, let's talk about scale and what we need to achieve with Snapchain. If you look at a network like X, they're probably doing something on the order of 100,000 to 1,000,000 transactions per second. We define a transaction as sort of any action that a user takes. So if you post something, if you delete a post, if you like something, follow someone, these are all different kinds of transactions. And X is roughly in the 100K to 1,000,000 range, extrapolating from public data that's out there. Snapchain today probably ranges from somewhere between 10 and 500, or the precursor to Snapchain, which is what Farcaster uses, is sort of 10 to 500 transactions per second. That's where we've been. And we're trying to design Snapchain to get to 10,000 transactions per second. So that gives us a lot of headroom to grow and gives us the infrastructure we need to get to the next order of magnitude of user growth. And in this video, we'll first talk about how we get to 1,000 and then kind of lay the path out from there to 10,000. So coming back to transactions, we'll look at this add post object, which we saw in one of our earlier videos, where this is a message that just adds hello world to the network. And pretty much everything that the user does is a transaction. So you'll have lots and lots of these little messages floating around, and each of these changes the state of a user's account and says, hey, this person has now said hello world or liked this post or whatnot. And the way each node keeps track of it, it uses this data structure called a Merkle trie, and we'll kind of walk through an example of how that would work. So let's say that Alice makes a new account. There is now remember, this is a blockchain transaction. Accounts are created on the blockchain. So there's something that happens that registers as an FID to Alice, and that transaction gets bundled up into Snapchain, and now Alice's state, which we represent with this circle and this line here, now has that one transaction which represents that she's opened her account. Now this is a Merkle trie, which means that each object that's inserted into this trie also produces a root for the trie, and if we add or remove any of these things, the root changes. So it's an easy way to checksum or compare two different tries very efficiently to see if they have the same messages without walking through all of them. And we'll see why this is important in a bit. Now if Alice adds a message that says hello world, so she adds this message, it gets broadcast, this is now added to her state. So Alice now has this root, but there are two objects under the root. There's the create account and then the hello world message, and now her state changes, or her root changes to represent that. And let's say the third thing Alice does is delete the hello world message. This is actually fairly common in social networks. People will post and delete things, like and unlike things, follow and unfollow. So there's a lot of back and forth or flapping of data. And what happens in this case is when the node sees the remove post message, that is Alice has deleted this, it can actually safely drop both the remove post message and the original add post message. And the nice property of this is the amount of data that the trie has to store has now been reduced. We've actually been able to eliminate some of this data and don't have a lot of this back and forth, which is a really nice sort of compression property that allows us to only store exactly the data that we need and nothing more. No history, no prior data, and all of this stuff. And each user has their own trie, but we also sort of build this global trie, which is a trie of all tries. And that's kind of the state of the node, right? So if you think of each Snapchain node, it's got a trie for each user, and then it takes each user's sort of root and then makes a new trie out of that. And so there's this global object that holds all of the messages in a user. So if you want to say, hey, what are the posts that Alice has? We would go down to this object, we'd sort of filter all these messages and return the posts, and that's the list of what Alice has. And every message sort of creates this insertion operation where you push it into the trie, you figure out where it goes, you change all of the parent tries, and now you have the new trie. Okay, the way messages flow through the system is we sort of bundle them up into blocks for convenience. So you can sort of model this as like every so often, maybe every couple of seconds, a new block is produced with a whole chunk of new messages. So this is like what Alice said, what Bob said, what Charlie said, and each node is given a block of messages to process. This is sort of where the block and blockchain comes into play with Snapchain. And what happens here is each block, when the node takes and processes these messages and sort of applies each message to the trie, it ends up with a new trie. So in this case, we'll say that the first message actually deleted one of Alice's messages. Like we saw earlier, this one maybe just removes a prior message. The middle message is actually Bob's, which is denoted in blue, and it actually adds a message to his trie, so you now sort of have three. And then on the last try, you have sort of Charlie's message, which is maybe it replaces it. So even though Charlie had two, this new message comes in and replaces one of the prior ones. So you can sort of see that like when a new block comes in, it can actually increase the state, it can decrease the state, or it can keep the state the same. All sort of possibilities can happen as blocks are processed and as the state trie increases. Now, one really nice property about how Snapchain works and the nature of the messages is the messages contain the entirety of the state. And we'll kind of contrast this to blockchains to explain what the difference there is. So in a blockchain, let's say Charlie's balance is 10. You need to know that, at some point Alice had the $10, sent it to Bob, Bob sent it to Charlie, and now Charlie's is 10. You need this whole train to establish that Charlie has the right to have 10, and you need to be able to trace it all the way back to the origination, something that created the $10 or the 10 ETH or Bitcoin in the system to begin with. In a social network, that's not the case. If Alice says hello world, that is the genesis message, and that is the only state you care about. That message contains everything that we need in order to represent that Alice has said this message, and so the history is not really necessary. This is really nice because it means we can prune a lot of the old data that we don't need, which is really helpful for scalability. So in this case, what this actually means is once we process a block, theoretically, we no longer need the block. We have all the data, we've processed it, we've stored the bare minimum set of data that we need in this trie, and then we've sort of gone ahead and dropped everything else. This is a big contrast to blockchains, which often have to store lots and lots of historical state, and state tends to get very bloated. And we've actually made this very, very efficient, which is we've said two things so far. One is certain operations can cancel each other out, and when that happens, we can actually elide both of those from the network and save space. But even beyond that, the blocks themselves can be erased over time as you move the state forward, and once you have confidence that these changes have propagated across the system, because we don't need to store all of this to validate. Each message is self-authenticating, and so you don't need a history of everything that happened. You only need the set of messages that make up the current state. And this helps us be much more efficient than blockchains, which is important because social messages actually carry a lot more data than blockchains do. And so all of these optimizations help keep the amount of storage that's used on these nodes fairly limited, which lets us get to a high volume or high transaction throughput on the network. And this architecture that we built, well, like a single node has to get messages, insert them into the Merkle trie. There's sometimes side effects that have to be run through, but we think that with all of that, we can probably process between 1,000 to 2,000 messages per second on a single node without a lot of optimizations. So at a baseline that is, quite a bit more than the current Farcaster network and gives us a lot of headroom to scale. We'll talk about how we go from the 1,000, 2,000 mark to the 10,000 mark, which involves sharding. But before we do that, we're going to do a quick segue in the next video to talk a little bit more about blocks. If you are familiar with blockchains, you're probably asking a lot of questions right now, like how are these blocks produced, who makes them, how can you actually erase blocks and not have syncing issues? And we'll get into all that in the next video before we go to the sharding section.